Previously, in the video about representation and splitting, we give a way to recharacterize representation. So we show that to say that alpha is represented by the quadratic form in V is equivalent to saying that V splits as follows. Now we'll give another way to rephrase this. This turns out to be equivalent to saying that this space is isotropic. But let's first explain what this space is. In particular, what is the quadratic form on this space? Say we already have a quadratic form Q on V. We want to extend this to the quadratic form to this space, right? This space is just a direct sum of V with some span of a vector, and that vector has to be orthogonal to V. What we mean is that we should extend the form in such a way that under that new bilinear form, this vector is going to be orthogonal to V. And also, the quote-unquote norm of this vector is going to be minus alpha under this new form. With that restriction, there's just one way to really extend this Q, the quadratic form here, to this new form. Let W be a vector in this big W, then we can write it as the sum of some vector in V and a multiple of this W naught. Now, if we expand out this Q tilde of W, then we see that because we require the V to be orthogonal to W naught, these terms vanish, right? And this should agree with the quadratic form on V. So this is just QV. And finally, these terms here, we know that the quote-unquote norm of W naught should be minus alpha. So this is just minus alpha of C squared. And thus, we have a unique extension of Q to this W. Alright, so now let's come back and let's show that V represents alpha if and only if this space is isotropic. So let's show necessity. Well, suppose V represents alpha, then as we mentioned before, this means that V splits as follows. Well, indeed, if alpha is represented by some V naught in V, then the span of V naught turns out to be regular, so we have that decomposition. Now, but then this direct sum will contain this space, which we have shown before to be isotropic. Actually, it's isometric to the hyperbolic plane. So then V itself must be isotropic. If you don't remember how we got that this space is isotropic, we can review a bit. So let's say that alpha was represented by the vector V naught, and we already have minus alpha is represented by W naught, right? Then the claim is that the quote-unquote norm of these vectors are going to be 0, but not both of them can be 0 though, because V naught and W naught is non-zero. So one of these is non-zero, but their norm is 0. Well, so why are this norm 0? Because that's just because of the calculation we did before. So imagine here we replace this V by V naught, right? So we are trying to compute the norm of V naught plus just W naught. C is plus or minus 1. Then this is alpha, this is minus alpha, so then they add up to 0. And thus we see that if alpha is representable by the quadratic form on V, then this space is isotropic, and the main reason is that because then it contains inside this isotropic space. Okay, now we're gonna prove sufficiency. So let's say that this space is isotropic. We wanna find a vector that represents alpha. To say that this space is isotropic means that we can find a non-zero vector in this space whose norm is 0. But if we write the vector in this way, this is the V component of it, and this is the W naught component, then by our previous calculation, this norm is just this. So we know that the norm of the V component is going to be alpha times C squared. And then we are done, because from this we can scale the vector V down to get something with norm alpha. And so V over C actually represents alpha. But there is a caveat here. We can only do this scaling if C is non-zero, right? So what if C is actually 0? Well, no problem. If C is 0, right, and remember this original vector is non-zero though, so this W is just going to be equal to V if C is 0. So if this is non-zero, then that means V is non-zero, but now the norm of V is equal to the norm of W, so the norm of V is 0. This means that V is isotropic. But we know that isotropic spaces must be universal because it must contain the hyperbolic plane. So V is universal. That's even stronger because if V is universal, it represents everything. So in particular, it represents alpha. And thus we see that V represents alpha if and only if this direct sum is isotropic.